First of all, obviously, I feel really honored to be asked to give a presentation today. One of all the things that have changed over the past year, the thing I miss most are actual live events and being able to mingle with people and see the people you're talking to and discuss things. I'm really hoping that next year I'll have at least some in-person events. So it's a very, very cautious hope at this point. One comment too, this is not a vendor presentation. I've used this title and so the logo, and I will say just a little bit about HPE products at the end. So there's a tiny bit of that, but the rest of it is fairly self-indulgent. So I hope you will bear with me as I reminisce a little bit about directives. Before I do that, I just wanted to spend a moment in remembering somebody who was a very important figure in the compiler community. So, of course, we don't have directives without compilers and without good compiler technology. And there aren't so many people who've contributed as much as Professor Gao has done. He's a professor at the University of Delaware for many years, and he died this last Sunday. So just wanted to say that. Okay, so when I was trying to think about what I wanted to talk about in this time, I was sort of thinking that I really did want to sort of raise a toast to directives, and the reason of that is, of course, that when people, especially in academia, of course, design new programming languages, come up with a new way of doing something, which may or may not see the light of day in terms of any usage. It's always a very exciting thing. People talk about it a lot, and a lot of attention, a lot of discussion, a lot of research around it if there is some momentum. But people have never talked in that same way about directives. So the directives are the things that actually get the job done, right? So I see them as being the pragmatic approach to supporting the needs, especially of communities such as that in supercomputing and high performance computing, where directives in various shapes and forms have been around really pretty much from the start. So what I will actually call the Cray Era, of course, there were Cray, Fujitsu, NEC, and other vector supercomputers, all vying, I suppose, for their market shares. But directives were incredibly important to enable productivity on those platforms. So from there, it was a small step to imagine that as new generations of HPC hardware came out, that directives should play a role there too. And so, sorry. Lost my pointer. So no surprise that that once what we think of now as HPC clusters, but at the time distributed memory parallelism, which was a new thing at the very end of the 1980s, early 1990s, and I realize that's before the time of many people on this call. That directives would again emerge. So. My personal history with directives starts at this time. I realize I'm dating myself there, but yeah, that's okay. I was actually very, very lucky to be as a student to be able to participate in quite a few of the meetings that defined high performance Fortran. So high performance Fortran, or HPF as it was known in the community at the time, was an effort to actually come out ahead of the curve in some sense and start defining directives for these new things, these new distributed memory parallel systems, before the individual vendors got together and came up with their own sets of directives. So in other words, there was an assumption at the time that the vendors would want to provide directives for programming, and the idea of this was let's get in, not my idea, let's get in and make sure that we have some portable directives before people roll their own. And there were companies such as CM Fortran who had some experience with not these kinds of machines, but certainly with high level extensions for Fortran that were mixed up in all of this. But it was overall, I would say in some sense, a doomed effort. So high performance Fortran, and just a side comment. This is before C++ was defined, so Fortran was the name of the game. It was really, thinking about other sets of or supporting other languages at the time. This was begun actually pretty early in the days when there was very little experience with distributed memory machines. And obviously, it's almost hard to imagine now. And it came up with a set of features that in some ways were pretty good. So the notion or the understanding that the data mapping was critical for performance was very clear. Excuse me. And the cornerstone of these particular sets of, or this particular set of directive was that the data needed to be mapped across the machine, and there were quite a lot of directives to support that and to enable different data mappings to be aligned with each other, so that you could be sure that certain things were on the same node of the system. And the compiler here was actually expected to do something that was Herculean. So in the default case, the application developer didn't actually have to say anything about how the computation was to be performed. So the implementation normally took the basic approach of saying that the work will be performed where the what's called the owner computes rule, where the left-hand side variable is located. And that turned out to introduce a whole raft of problems, not least of which was the fact that it was extraordinarily hard to compile, but also because the resulting performance was frankly impossible to understand. So the compiler work here was at least from the point of view of an application developer, some kind of magic or black magic. Something happened, and sometimes performance was good, and sometimes you had a 200x slowdown. So you could be anywhere, and it was extraordinarily hard to understand. So this particular effort was actually enormous in terms of the people involved. So there are many companies that don't exist anymore, such as DEC, Convex, and so on, regularly sent their representatives. So this was quite a large room of people, and a really major effort to define directives that people thought would be the mainstay of parallel programming for some time to come. And just an aside, many of the meetings were held at a hotel on a freeway somewhere in the Dallas area. And as a poor student coming from Europe at the time, I had to spend weekends there, and it was a bit of a dismal experience. But there was one other European who had to do the same thing, and had to do it twice a month, not just once a month like me, because he was taking part in another standardization effort, which happened to be at exactly the same hotel during the same years. And that was something else you might have heard of, called message passing interface, so MPI. So these things were actually going on in parallel at the same location, even at the same time. And I guess we know which one of those actually took off. At least in terms of the applications folks, the HPF was considered to be a failure. It was certainly not a total failure, for one reason being that there was a lot of compiler technology developed around this, which we've been enjoying and benefiting from ever since. So in terms of providing impetus to the compiler folks, it was very important. The other thing that was very important about it, or at least that gave it some longevity, was the fact that the Japanese actually persisted, and they actually came up with some extensions of their own. So they kept working on both the feature set and the implementations, and used it for some years. And it actually still exists in the form of, or at least partially exists in the form of Scalable MP, which is largely based on HPF features. So it didn't completely die away everywhere. And I guess that sort of says that persistence can really pay off. But it was in many senses of the word a premature effort. Very shortly afterwards, OpenMP was defined, and the initial definition there, of course, also focused on Fortran, which had been extended not much later. And the people who defined that were very anxious that that application developers might ignore it because HPF had been perceived as a failure, and so they worked hard to do what the application developers said that they wanted. And the key thing that was being asked for at the time was, we want features where we know what's going on. We want to be in charge. So this issue that you could write something and have no understanding of what the performance is, which also means you don't know what to do about it, had really burned people. So this is the origin, if you like, of the fact that OpenMP was very much focused on, and very deliberately focused on, providing features where the user is in charge, the user says what's going to happen. In other words, what we would probably think of as being prescriptive now. And of course, that actually has had a lot of success. The image here is actually from a salt dome, which is somewhere in the border of Texas and Louisiana. This was at the time the largest computation of its kind done by PP, and it was all done using OpenMP on a system that also no longer exists now, is the Origin. So OpenMP actually supported quite a lot of serious science for some years before the Origins were retired, and of course then went on to provide support for multi-core systems. And so things might have remained as platforms continued, of course, to grow in their core counts, unless things had been shaken up a bit. And this is a representative. Of course, there were many systems and many people pointing out the benefits of using GPUs, both in terms here, as Satoshi was saying, in terms of economics, but also for performance per watt. And and it was another arguably pretty large architectural shift requiring attention. And it turned out that some people, especially Francois Baudin, who was at another wonderful company that no longer exists called CAPS, had been thinking about embedded systems and other devices for some time, and exploring extensions. At the time, he had his own features, and then explored how they might fit in with OpenMP to actually provide directives for, again, reasonably productive programming on these devices. Somebody else whom you will know very well who was thinking early about this was someone called Michael Wolff. Okay, and then the rest really is, so to speak, history. I pulled this from a very old presentation, which I think was in 2013. So talking about the fact that by that stage, the HPC systems had pretty large core counts, were increasingly hybrid, and that people were increasingly concerned about how to program them. And of course, into this mix jumps, let's just say, PGI, Cray, NVIDIA, and so on, with OpenACC. So that was announced at Supercomputing. I still remember them sitting in the audience, hearing Jensen Huang talking about it, and explaining that this was going to be the new way to go. And pretty shortly thereafter, there was actually a pretty good time, I would say, for an OpenACC, in the sense that there were several compilers out there supporting it, supporting the initial version. There were a couple of research compilers. So OpenACC, I think, needs no introduction. OpenUH was something that we developed for several years in our research group in Houston, and GCC too. So pretty good support in those early days. I think I'll just skip this, but we had a lot of fun actually trying to develop this and trying to outperform PGI, because that was what you wanted to do as an academic, was figure out how we could do anything better than PGI. So and also learned that things like performance portability, which I think as a term or as a requirement was certainly pretty new at the time, that the devil's in the details, and it's kind of hard to accomplish. So nothing's new under the sun. So it was just my very short take on where directives have come from. in the interest of time, I can't really say much more, but I don't want to say, obviously, we all know that this is a sort of some obvious things, but applications are around for a long time. The application developers are, by and large, very cautious and conservative for very good reason in terms of the languages and models that they adopt. Directives have been, I think they've simply proved their point, right? They've been around right from the start. They've been extremely important, especially with respect to enabling productivity. Have also shown that they can be used to get scalable performance on a wide variety of different architectures. So spanning so vector systems through multi-core systems, or through distributed memory through multi-core systems, and now also through accelerators. So I'm very curious to know what's coming next. Obviously, I think there's some interesting things where we may or may not need to act. And one of them is, I'm sort of curious to see how people actually deploy multiple GPUs on the node. I suspect that OpenACC won't have to worry about that. I believe OpenMP will have to. But the really interesting thing, of course, given that the enormous rate of innovation and hardware nowadays, is that it would be very interesting to see what new platforms arise that will want to put the directives onto. So in other words, what new targets there'll be. And what new kinds of users there may be. So especially users coming through the ranks now who will probably, or many of whom I think will demand productivity much more forcefully than people have done in the past in high performance computing. So with that, I want to spend just a few minutes. I hope I have time. I think I'm just about out of time on my clock, so I'll be very, very brief about this. The last point, because we want to have users who successfully deploy directives and obviously have good experiences, and that implies that the compilers have to be solid. Obviously need a good choice, and we also need to have good ecosystems. So I'm an academic at heart, and as you heard, I've just joined HPE Cray, and one of the great things about this is finding out that HPE, of course, acquired Cray, that they very much appreciate the existing Cray programming environment and want to see that evolve and continue to be an important programming environment for high performance computing. And so I'm going to say just one or two things about this so we can wrap up. The Cray programming environment, and I'm expecting that many of you have much more familiarity with this than I do yet, so which is one reason I won't say too much now, but they support a variety of programming models. They, of course, provide a complete environment in terms of tools for the application developers. And as unfortunately somebody stole my thunder yesterday, so I suspect that this has already made the rounds. But in the spring, the Cray or HPE Cray people announced that they are resurrecting OpenACC that had been frozen at version 2. But it is now back, and people are working on it, working hard on it, and with the goal of bringing that up to speed and providing full support for that. And by full support, I'm going to just skip through some of these because I think we're out of time. That will mean providing not just, we'll say just in quote marks, the compiler, but also the full programming environment. And I think that's incredibly important for application developers, because I don't think you can ever have too many tools to support any programming language or programming model. The performance analysis tools, or CrayPad, if you're on them earlier, provide a particularly rich set of features for analyzing, understanding how your code is being translated and also how it's behaving. So I'm going to skip just a couple of slides with some examples of its use with OpenACC, just so that you know it's there. It's already working. And I'm very much looking forward to further evolving this and making sure that we have not just a good, but a great programming environment on many HPC platforms via the HPE Cray environment. Okay, so if you remember, Cray was there at the start, went away and came back. hence the Back to the Future. That's it from me.